Now for something completely different, I'm going to talk about lunar geophysics. I'm Matt Siegler. I'm at PSI located at Southern Methodist University in Dallas. So we're going to change subjects a little bit here. Basically wanted to take this opportunity of this conference to advertise this paper that came out during LPSC, so a lot of people didn't see it because we were all paying attention to LPSC. So it seemed like a pertinent one to bring up again at this conference. This is work by this whole team here, especially Rich Miller and James Keene, who did a lot of the work you're going to see here. So ask them about questions. Rich is here, James isn't. So the conceptual overview of what we're seeing is that there seems to be striking evidence that the distribution of hydrogen at the poles of the moon is actually controlled by ancient polar wander of the moon that's caused by the thermal evolution of the Procellarum creep terrain. Okay, so it's like a big conglomeration of a bunch of things, but we've pieced this story together and it seems to hold together pretty well. I'm going to go through some of the evidence for that. So overview of what we're going to go through here. So the lunar epithermal neutrons show strong off-polar enhancement of hydrogen at both poles, that these deposits are approximately antipodal to each other, and I'll get to what I mean about that in a little more detail, because of course they're both at the poles, right? And then thermal models including a past pole, so a past rotational axis separate from the current rotational axis of the moon, seem to correlate better with the neutron data, implying that the moon has changed its spin axis by about 6 degrees. And the motivation for the moon to cause this reorientation fits very well with the location and magnitude of thermal anomalies that we expect from the Procellarum creep terrain's evolution. Okay, so here's the general picture we're going to be starting from. So this is work that Rich did back in 2012 and has done some updates since. What we want to look at is 4 key features here, and I'll go through each one of them one by one here. So the first key feature is that the polar maxima are not actually at the pole, right? You would expect at least the whole distribution to be sort of symmetric around the pole itself. You know, topography controls it a lot because you don't have equal distribution of shadowed craters everywhere. But what we noticed was odd was that the highest concentrations, which are marked by these dots here, are actually offset from the pole at about 5.5 degrees. And they're about 5.5 degrees at both poles. All right, we knew that for the South Pole, because that's why we crashed L-cross there, was it was the highest concentration of hydrogen near the South Pole. People really hadn't seemed to look at the North Pole as much once we decided to crash at the South Pole. Another interesting thing is, although we always think of the South Pole as being the, oh, it's got all these big craters, there's probably a lot more ice there. The actual hydrogen concentrations at both poles are pretty much the same magnitude. And these are a contour of 75 ppm hydrogen from the Lunar Prospector neutron spectrometer data. The hydrogen doesn't correlate well with where we'd expect it to be from the current thermal environment. And this was really my part of this work was we do these models of where ice should be stable. So this is where ice would be if the moon were like Mars. If you had, plentiful supply of water that was coming everywhere, this is where you would expect to freeze it out. This is what that would look like in neutron vision. Okay, that the resolution that we have from the Lunar Prospector neutron spectrometer. And basically what we're arguing is that this map doesn't really look like the data that we see, like this. So the models don't do a horrible job matching, but they don't do a very good job either. And this is, now with the data from Mercury, we could see like, okay, we do these same thermal models for Mercury, and the ice is exactly where we expect it to be. So it's really surprising that we get such a difference here on the moon. So it demands an explanation. And then we'll go through this point, what I mean by the hydrogen is antipodal. So part of why we haven't noticed this as a community is the way we project maps. If you look at the moon as if it were a globe with the Earth facing side down on both, you would project the maps like this. And you can see that there's this odd coincidence that this position here of the highest concentration is sort of on the opposite side of the moon from the other. You could almost draw a line through the moon around this old, what we're calling the old spin axis, and it would connect those dots almost exactly. A better way to prove that is to look at how these distributions statistically correlate. So this is work Rich did as well. So we have these these contour distributions, and what we're going to do is just rotate them around. And ideally, if the distributions as a whole, so not just these highest concentration points, but the distributions of a whole, if they were antipodal to each other, you'd get the best correlation around 180 degrees. This is what we get. We get a 8.3 sigma correlation of these two distributions with each other. Now you might say, oh, well, that's just because of the thermal environment or because of topography. But if we take any of those other quantities, such as, you might expect the yearly maximum temperature might control ice distribution, the ice stability models, take any of those other quantities and do the same study with them, and you see no apparent correlation with any particular longitude. Okay, so we have this high significance correlation that these two distributions are opposite to each other. And so now we need to find a good explanation for why you would have the ice on the moon, or the hydrogen on the moon. We shouldn't always claim ice, but correlating so well with this. And what we find is if we assume that the hydrogen is coming from ice or was originally deposited as ice, we can explain this very well with a model of true polar wander of the moon. So what is true polar wander? Okay, so basically we're used to something like the Earth spinning like this. We always talk about, oh, the axis of the Earth moved or something, right? Normally we're talking about something like an obliquity change, which is a change in tilt, where the spin axis is still in the same location. The South Pole is still in Antarctica. True polar wander is a different beast altogether. It's where the position of the pole actually moves. So this would be like the South Pole being in Australia instead, or something like that, with the rotational axis. Obliquity changes are external forcing, like Milankovitch cycles, so it's Jupiter or Venus yanking on our planet in a way. True polar wander has to come from an internal redistribution of mass. So we have it on Earth because plate tectonics move. We think of it on Mars because Tharsis formed and formed a big bulge which wanted to migrate towards the equator. So you're changing the moment of inertia of the planet. And so what we're suggesting here is that here's the current spin axis, and the moon used to spin around this point, essentially. And that's what we're calling the paleopole. One way we can look at how to argue that, okay, ice deposited in that paleopole orientation would explain the distribution of hydrogen we see on the moon better. We could take our same, present day thermal models, but then it's a model, right? We can run it under any orientation in the past, and here's where ice would deposit if the moon spun around that point instead. And we can combine those together to say, hey, where would, if we took ice and said we deposited under the old condition, where would it be versus if we posited under the current condition? And what we get is if we take a mixture of ice from this deposited prior to the polar wander with ice that's stable in locations today, we can actually get a much better match for the data. And here you can see, here's the neutron data again. So we're comparing this match here to this match here. So to briefly oversimplify that, it's essentially we're taking a Venn diagram of the two polar positions. Ice can be stable in craters maybe about 12 degrees or so away from the pole. all right, before you're really going to be directly illuminated for the most part. So it's, so all craters that could have ice fall roughly in that circle. And then all craters that could have ice today fall roughly in that circle. And so this is places where the sun never shined, okay? Despite the moon moving its spin axis, the sun has never illuminated these areas. And that seems to be a pretty good explanation for the ice. So now what would cause that motion? Well, like I was saying, it takes a change in mass anomaly. You either need to do a negative mass anomaly, like dig a big hole, or cause some density change, or positive mass anomaly by building a mountain or causing a bulge on the surface. And so we brought James Keen to work on all this. So he has worked with the Grail gravity models. And he basically said, okay, if we put positive masses in any of these locations or negative masses in any of these locations, we can cause the pole to move along, between these two locations that we're predicting from the hydrogen. And so we searched and thought, okay, well, maybe a positive mass anomaly like Moscoviense here. Okay, Moscoviense falls on our track. And you can see here is how much this changes this quantity, which is something related to the inertial tensor of the moon. And you can see that it's nice, it does something, but it doesn't have a big enough effect on the gravity field of the moon to actually cause a 6 degree or 5.5 degree migration like we're seeing. One thing that does fall directly in the path is the center of the Procellarum creep terrain here. So we have this large thorium anomaly here, which people have been working on for quite a while, nearly 20 years or so, have looked at, well, you have all that thorium concentration in the crust, it's going to have some effect on the temperatures in the mantle below and the thermal evolution in the interior of the moon. One of the best versions of that work is Mathieu Lanville, who was working with Mark Wozorek on this model. They basically took radioactive material, put it in the crust, started with an isothermal radial symmetric moon, and see how they heat up the mantle below. And what we did was then, if you could play the movie. So we then took this model and, well, James did put it into an inertial tensor model and saw how the moon would migrate its spin axis in response to this change in density in the lunar interior. And we basically trace out this path. Here's viewed from the Earth. So one of the interesting things is that the view of the moon from the Earth actually changes because of this. And then here's the poles. You could see essentially we're tracing a line through each poles along the elongation of the hydrogen deposits. Here's an example of one of those models of the path that we're going to take through from the old spin axis to the current spin axis. Suggests that the volatiles are old and predate this true polar wander. You can change the timing of this by changing the rigidity of the lithosphere as a function of time. So there's plenty of model space to change the timing of this motion. But we can constrain a few things, like that if the pole is moving from this spin axis to this spin axis, we can't have a lithosphere that's entirely strengthless, just that it can flex up entirely. So what does all this say about the water? So it says one of three things here. The ice predates true polar wander, or at least most of the ice, and we're seeing ice that has survived from most of those models. Like I said, they can change from what you assume about the interior, the flexibility of the lithosphere. But we're seeing ice that's probably survived 3 billion years or so. So we need an explanation for that. Another thing we might be seeing is that as the pole migrated, you had preferential deposition of ice along the path. So when a comet hit the moon, it froze out closest to the pole. And the third possibility is that this is just sort of a stunning coincidence, that this distribution has another easier explanation, but the fact that it lines up with the peak AT, and that we would have, if we just had done the inertial tensor models prior to this with the thermal evolution models, we would have predicted this. So the fact that we're seeing it from both ends seems pretty surprising to be a coincidence. And we'll stop there with summary. So let me know if you have questions. Thank you.
Thank you for a wonderful talk. I heard two things. One was that there was like roughly 50-50 water from this before the polar wander and after, and then you said most of the ice. So I was wondering if there's a different water ice fraction that came out in the end, because I think both there was like 52-48, or there was some number near 50-50, and I may have missed something.
Yeah, so there are lots of ways you could get you can match the distribution by mixing the old ice stability maps and the new ice stability maps. So we just went with the simplest thing, was taking the two maps and seeing what ratio of them matched the best. You could do other maps where you say, okay, we're going to take only the places that have been in shadow the entire time through the two, and just doing that straightforward, you don't get quite as good of a match. So what we're essentially, so maybe Rich, you have a comment on that?
And so take those percentages with a little bit of a grain of salt. The real conclusion is that the existing hydrogen distribution being the current thermal environment being responsible for the hydrogen distribution can be excluded statistically to a fairly high degree of confidence. To really get at your question, what percentage is old and what percentage is new, we really need to take these models, and there's still some unknowns, but follow the full path and model the whole thermal environment over, the 3 billion years. So I wouldn't put a whole lot of stock in the 47 versus 53%, but what you can take away is that the current thermal environment cannot be the sole driver of the current hydrogen, and that some of that hydrogen must be ancient. That's the real takeaway.
That's a good summary. Thanks.
Okay, we'll take one more short question.
Yeah. So, why were you looking only at a single individual event as a cause for the mass anomalies to move the axes?
I mean, so we had James had a previous paper there looking at the migration from each individual large basin impact. So we had sort of looked at those in a time sequence, and we actually, James is working on that as a follow-up to this project, is to look at how the pole would have migrated from individual impacts. But we only have relative timing with them, really. It's not exact. But yeah, this would be a long, slow individual impact. So it's just our migration.